Good morning. So, we are learning discrete mathematics. Today's topic under discussion is Unit 4, which comprises of algebraic structures, algebraic system, properties, semigroups, groups, monoids, homomorphism, group codes and their applications. So, this is the target. So, let us start our discussion. So, our topic is algebraic structures. Here, the notations being used are S represent non-empty set, star represents a binary operation. Unless otherwise specified as multiplication, it is in this topic binary operation. This star can be plus A plus B. This star can be multiplication A star B, like that. If it is an algebraic structure, it holds closure property. And what is a closure property? There are two elements, say A and B, belonging to a set S. So, the multiplication or the binary operation rather of those two, the resultant will also be part of that set. That is a closure property. So, if the closure property is held, then it is an algebraic structure. An algebraic structure is a semigroup. An algebraic structure is a semigroup if it holds associative property. A semigroup is a monoid if it holds this property. A binary operation E is equal to E binary operation A, which is equal to A for all A belonging to S. Here A indicates an identity element. For example, 10 plus question mark is equal to 10. So, here question mark is rather we want to find out the identity element. So, 10 plus what will be equal to 10? So, naturally it is 0. So, for this case 0 is the identity element. A monoid is a group. A monoid is a group if it holds inverse property. And what is this inverse property? Let us say A binary operation B is equal to B binary operation A, which equal to identity. So, B will be called as the inverse of A. B is represented as A inverse. Let us say we want to find 5 plus inverse element is equal to identity. So, here minus 5 will be the inverse element. So, the value of B will be minus 5, which is the inverse of A, which is 5. So, a group is an abelian if it holds commutative property. A group is an abelian if it holds commutative property, and commutative property we all know A star B, A binary operation B is equal to B binary operation A for all A comma B belonging to the group. So, the journey starts with algebraic structure. If it is an algebraic structure, closure property, then check if it is a semigroup. Semigroup is an algebraic structure holding associative property. Then check for monoid. Monoid is a semigroup with identity element. Then check group. Group is a monoid with inverse property. Then check abelian. Abelian is a group with commutative property. Now, we have been referring the properties. So, this is a commutative property. Say A binary operation B is equal to B binary operation A for all A comma B belonging to A. This is an associative property. Even if we take this as a multiplication, let us say A star B star C is equal to A star B star C. Identity. What is an identity property? Okay. So, element E will be called as an identity element if this is held. A star E is equal to E star A is equal to E. And remember, identity element is unique. The next property is inverse property. The next property is inverse property. A star B is equal to B star A is equal to E. Here B is an inverse of A inverse. Now, after that, what is a sub-semigroup? Sub-semigroup naturally is a semigroup, right? So, let us say S comma star is a semigroup. Then T comma star and let T be a subset of S. If T is closed, then T comma star is called as a sub-semigroup. Similarly, submonoid. A monoid will be there, inside that submonoid will be there. Let us say S comma star is a monoid and T is a subset of S. If T is closed and if it holds this property, identity belongs to T, then T comma star is called as a submonoid. In a group, the properties which are held in a group are: identity elements are unique, inverse of an element is unique, cancellation law holds, say left cancellation and right cancellation. For example, A star B is equal to A star C can be applying the left cancellation law, A will be cancelled and what remains is B equal to C. Similarly, using right cancellation law, A star C is equal to B star C. So here C will be cancelled and A is equal to B will be retained. Similarly, A star B whole to the power of minus 1 will be equal to the B to the power of minus 1 star A to the power of minus 1. In a group, the identity element is its own inverse. The number of elements in a group is called as the order of the group. If the order of the group is finite, then it is called as a finite group. Let us take a small example here. We have non-zero real elements. How we represent real elements? R. And how we represent non-zero real elements? R star. So we have to check whether it is a group or not with respect to multiplication operation. So our binary operation here is multiplication operation. Okay. So as it is a non-zero real number, it will be showing closure property, so it is an algebraic structure. It will be showing associative property, so it is a semi-group. It will be having an identity element, so it is a monoid. It will be having an inverse element, so it's a group. It also holds commutative laws, so it is an abelian. So this real number, non-zero real number, with respect to multiplication operation, is a group as well as it's an abelian group. But suppose we have only R, which is a real number including 0, okay, with respect to multiplication. So it does not hold the inverse property because 0 has no inverse. So R is not a group. R is not a group. Similarly, let us say we have Z comma star, where Z is an integer, okay, and this is our operation, n star m is equal to max of n comma 1. So for this case, it is an algebraic structure, it is a semi-group, but it is not monoid, as there is no identity element with respect to this max of n comma m. Let us look at this composition table, which is also called as cayleys table. First, let us just understand how to design the composition table or cayleys table, and what is the purpose of this design. We want to check the properties, whether they are algebraic structures, whether they hold associative, commutative properties, whether they are having identity, inverse elements, and so on and so forth. So first let us see just the design. Okay, A is a set comprising of these elements minus 1, 1, minus I. So I have to design what? I have to design a composition table. I have to design what? I have to design a cayleys table. So what I will be doing is these 4 elements minus 1, 1, minus I. Okay, I will be keeping them as column headers as well as row headers. So minus 1, 1, minus I. Similarly, row headers as minus 1, 1, minus I. So now this becomes a grid or kind of a matrix wherein we have to fill in this 1, 2, 3, 4, 1, 2, 3, 4, 16 elements we have to fill. How do I go about this? I just need to check what is the operation being mentioned here in the cayleys table. The operation being mentioned here is a binary operation, but it is a multiplication operation. So let us check. Minus 1 multiplied by minus 1 is 1. Minus 1 multiplied by 1 is minus 1. Minus 1 multiplied by minus I is I. Minus 1 multiplied by I is minus I. Next, let us go to the next row. 1 multiplied by minus 1, minus 1. 1 multiplied by 1 is 1. 1 multiplied by minus I is minus I. 1 multiplied by I is I. Let us go for the third one, minus I. Okay. Minus I multiplied by minus I. So minus I multiplied by minus I is how much? I square. And what is the value of I square? I square is minus 1. So I have kept here 1. I square is minus 1. Okay. So yeah, I square is minus 1. So it should be minus 1. Let me check once again. The third element is minus I, and with minus I into minus 1 it is I. Minus I into 1 it is minus I. Correct. This is I and this is minus I. Then minus I into minus I. Minus I into minus I will be I square, which is equal to minus 1. Minus I into I. So minus I into I will be minus I square. So minus I square will be 1. So it is 1. Similarly, last element is I in the row. So I multiplied by minus 1 is minus I. I multiplied by 1 is I. I multiplied by minus I is minus I square, which is equal to 1. I multiplied by I is I square, which is equal to minus 1. So this is my composition table or cayleys table. Now I want to check the properties whether this cayleys table or composition table holds the closure property. So whether it holds the closure property, yes. How? I need to check my elements. These are my elements in the set, minus 1, 1, minus I, and I need to check the resultant elements. If you check all the resultant elements, they also are same. Okay, so nothing is beyond this set, so it holds the closure property. Next, whether the associative property is held, yes. This is associative property is held. No way of checking here using the cayleys table, but associative table is held because these are real complex numbers, and for them, for this operation, it is held. Let us go for the third, whether identity is held. So what is identity? A star E should be equal to A. The identity is held or not, we need to check. How I need to check identity is held or not? So let me check here. Here, for identity, what I have to do is I need to check the rows which are matching and I need to check the columns which are matching. So let us see. Row number 1 is minus 1, 1, minus I. 1, minus 1, I, minus 1, not matching. Minus 1, 1, minus I, it is matching. So row 1 and row 3 are matching. If row 1 and row 3 are matching, so we have to take the extreme element of the row. That becomes the identity. So the extreme element of the row is 1. So 1 is the identity for this row. Similarly, I need to check which columns are matching. If I check which columns are matching, minus I, minus I. Let me check which one is matching here. First I check which row has matched. This row has matched with this. So similarly I have to check the column, right? Minus 1, 1, minus I. So minus 1, 1, minus I. Same thing. Column 1 and column 3 are matching. So I have to take the extreme element of the column. What is the extreme element of the column? 1. So 1 is the identity element. So monoid property is also held, identity property is also held. Whether it holds the inverse property or not. So to check whether it holds the inverse property or not, what is inverse property? A star B is equal to B star A is equal to E, okay, which is an B is an inverse here, E is the identity element. So you can see here the one which we have marked, this minus 1, minus 1, okay. So this will be holding the inverse property. Similarly, this minus I, this minus I. So this will be holding the inverse property. The last thing to be checked is whether it is commutative or not. Whether it is commutative or not. So for that, we need to check whether it is abelian or not. So for that, what we have to do is we have to draw from this binary operation. We have to draw a diagonal. After drawing the diagonal element, we have to check there is a symmetry in rows and columns or not. So minus 1, minus 1. Is it not? Then 1 minus 1, then 1 minus 1, then minus I 1 minus 1, minus I 1 minus 1. So I minus I, I. So I minus I and 1 1. So it is holding the symmetry. That's why it is commutative also. So this was, we'll continue with this Cayley table and composition table examples in the next session. Thank you.